There is something passing through you right now, something so invisible, so indifferent to matter, that even while trillions of it move through your body every second, you will never feel a single one. It comes from the sun, crosses the earth as if the planet were barely there, passes through bone, blood, steel, stone, and vanishes without leaving a mark. And yet this almost impossible particle has forced physics to confront one of its deepest questions. Is our best picture of reality complete, or is something fundamental still missing? In this video, you're going to understand what neutrinos really are, why physicists were driven to propose them in the first place. I say, how they were finally detected, and why these almost untouchable particles may point beyond the standard model itself. If you enjoy clear, informative, and deeply researched science content like this, subscribe to the channel and click the bell icon so you never miss the next video. The strange thing about the neutrino is not just that it is hard to detect. The truly strange thing is that the only reason anyone knew it had to exist at all was because the math refused to behave without it. Long before anyone saw direct evidence of a neutrino, physicists were facing a problem serious enough to threaten one of the most trusted rules in all of science, the conservation of energy. That rule sounds simple, but it is one of the pillars holding modern physics together. Energy does not appear from nowhere, and it does not disappear into nothing. In every collision, every chemical reaction, every nuclear event, the total energy before and after must balance exactly. Not approximately, not most of the time. Exactly. It is one of those principles that has survived every experimental challenge ever thrown at it. And that is why the problem that appeared in beta decay was so disturbing. In certain radioactive decays, a nucleus would eject an electron. The nucleus itself would recoil. Physicists could measure both. They could add up the energy carried away by the outgoing electron and the recoiling nucleus, and the total kept coming up short. Not by one fixed amount that might have suggested a faulty instrument or a missed calibration, but by a different amount each time. The missing energy varied from one decay to the next, as if something unseen were taking a random share and slipping away before anyone could measure it. That left only two possibilities. Either the conservation of energy was not truly fundamental and quietly failed inside atomic nuclei, or something real was escaping detection, something produced during the decay, carrying away the missing energy and momentum, yet passing through every instrument in the lab without leaving a signal. The first possibility was disastrous. If energy conservation could fail, then physics would lose one of its most dependable foundations. Every prediction built on that rule would become uncertain. Every equation depending on it would rest on unstable ground. So physicists looked toward the second possibility. If the numbers did not balance and the law still held, then something had to be carrying the missing share away. That was the path Wolfgang Pauli chose in 1930 when he proposed the existence of a new particle. He did not present the idea triumphantly. He described it as a desperate remedy. That choice of words matters because it shows how uncomfortable the idea really was. He was not introducing a new particle because he wanted to expand the particle zoo. He was doing it because the alternative was worse. If conservation had to survive, then nature had to be hiding something. Pauli suggested a neutral particle, one with almost no mass, produced alongside the electron in beta decay. It would carry away exactly whatever energy and momentum were missing. It would have no electric charge, which explained why ordinary detectors could not easily catch it. And because it would interact only extremely weakly with matter, it could escape the nucleus, the detector, the lab, even the Earth itself, without being stopped. That proposal solved the bookkeeping problem, but it opened a far stranger one. What kind of particle can pass through matter as if matter barely exists? What does it even mean for something to be so disconnected from the world of ordinary objects that entire planets offer almost no resistance to it? To answer that, you have to stop thinking of particles as tiny, hard dots moving through empty space. That picture works just well enough to be useful in everyday explanations, but the neutrino lives much deeper than that. At the level where quantum mechanics and relativity both matter, particles are not best understood as little objects. They are better understood as excitations of fields, disturbances in structures that already fill space. And that shift in perspective changes everything. Because once you begin to see the neutrino not as a tiny speck, but as a disturbance in a field that barely couples to the fields making up ordinary matter, its ghost-like behavior stops looking like magic and starts looking like a clue. A clue not only about what the neutrino is, but about how reality itself is built underneath the visible world. To understand why the neutrino behaves the way it does, you have to look more closely at what conservation laws are really telling us. These laws are not suggestions. They are exact constraints the universe follows without exception. Every time you throw a ball, every time two objects collide, every time energy changes form, the accounting is perfect. Momentum transfers precisely. Energy balances exactly. Nothing appears from nowhere, and nothing disappears without going somewhere. That is why the beta decay problem was so serious. A neutron inside a nucleus transforms into a proton and emits an electron. The nucleus recoils, and both can be measured. But when physicists added up the energy and momentum, something was missing. Not a fixed amount that could be corrected with better instruments, but a continuously varying deficit. Each decay event produced a different shortfall, as if the missing portion was being divided up in unpredictable ways. There were only two logical interpretations. Either conservation laws were breaking down inside atomic nuclei, or something else was carrying away the missing energy. The first option would have undermined the entire structure of physics. Every theory, every calculation, every engineered system depends on conservation holding true. If it failed even occasionally, the reliability of the entire framework would collapse. So physicists followed the second path. If the numbers do not balance and the rule must still hold, then the missing energy must be real and must have gone somewhere. That somewhere had to be a particle. Not one that had been detected, not one that left visible traces, but one whose properties were already defined by the deficit itself. It had to carry exactly the missing energy and exactly the missing momentum in every event. In that sense, the neutrino was not guessed, it was required. Its characteristics were written into the imbalance long before anyone observed it. Conservation laws had effectively described a particle no one had ever seen. This is what made Pauli's proposal both powerful and uncomfortable. He was suggesting a particle defined almost entirely by its invisibility. It had no electric charge, so it would not interact through electromagnetism. It had almost no mass, so its absence from measurements could be explained. And it interacted so weakly with matter that it could pass through detectors without leaving a signal. At the time, this was unlike anything physics had ever proposed. Every known particle had been detected through some measurable effect, tracks in a chamber, or ionization in a detector. The neutrino, by contrast, was introduced as something that might never be directly seen. Enrico Fermi took this idea further. He built a mathematical theory around it, giving the particle its name, neutrino, meaning little neutral one. Sas edinocerum tuum naimtum. More importantly, he described how it could be produced during beta decay through a new kind of interaction. Not electromagnetic, not strong nuclear, but something weaker. A force capable of producing particles, but so feeble that it rarely caused interactions afterward. This was the early description of what we now call the weak nuclear force. Fermi's theory did something crucial. It did not just explain the missing energy. It predicted how the electron's energy should be distributed in beta decay. Instead of a single fixed energy, the electron would share the available energy with the neutrino, producing a continuous spectrum. The randomness in electron energies was not random at all. It was the signature of three particles sharing energy, two visible, one invisible. The neutrino had left its fingerprint in the data, even though it had not yet been detected directly. For decades, that was enough. The neutrino was accepted as real because its effects were consistent, measurable, and necessary. But no one had actually caught one, and that raised a deeper question. What kind of particle is so detached from matter that it can pass through entire planets without interacting? The answer is not about size or speed, it is about interaction, specifically which forces a particle responds to. Every particle interacts through certain forces and ignores others. Those interactions define how it behaves in the world. The neutrino carries no electric charge, so it does not interact through electromagnetism. That means it does not feel electric or magnetic fields. It does not participate in chemical reactions. It does not bounce off atoms the way other particles do. The electromagnetic force is responsible for almost everything you experience: touch, light, structure, and the neutrino ignores all of it completely. It also carries no color charge, which means it does not interact through the strong nuclear force. That force binds quarks together inside protons and neutrons. It is one of the most powerful forces in nature, yet for the neutrino, it may as well not exist. That leaves only gravity and the weak nuclear force. Gravity acts on anything with energy, but at the scale of individual particles, its effect is extremely small. The weak force is the only interaction that meaningfully connects the neutrino to the rest of the universe. And weak is not just a name, it is a precise description. Even in environments flooded with neutrinos, interactions are rare. When scientists finally detected neutrinos in 1956, they had to place a massive detector next to a nuclear reactor, producing an enormous number of them. Hundreds of trillions passed through the detector every second, and still only a few interactions were recorded each hour. That is what the neutrino is, a particle that exists everywhere, constantly moving through matter, but almost never interacting with it. Not because it is hiding, not because it is blocked, but because it is fundamentally disconnected from most of the forces that govern the material world. And that disconnection is not just a curiosity, it is a clue, one that begins to reveal a deeper structure beneath everything we think we understand about matter and reality. What makes the neutrino even more unusual is not just how rarely it interacts, but how it fits into the deeper structure of reality itself. To understand that, you have to move beyond the idea that particles are tiny objects moving through empty space. That picture is useful, but it breaks down completely at the level where neutrinos operate. In modern physics, a particle is not a solid dot. It is better understood as a disturbance in a field. And a field is not an object. It is a property that exists at every point in space. Temperature is a simple example. At every location in a room, there is a temperature value. It is not something sitting in one place. It is distributed everywhere. Quantum fields work in a similar way. Each type of particle corresponds to its own field that fills all of space. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. And the neutrino is an excitation of the neutrino field. When energy disturbs one of these fields in the right way, that disturbance moves outward, like a ripple on water. The water itself does not travel across the pond. The ripple does. The field remains everywhere, but the disturbance moves through it. That moving disturbance is what we call a particle. This idea matters for the neutrino because of how its field connects, or more accurately, does not connect to other fields. Most particles interact through multiple forces because their fields are linked to others. These connections are called couplings. If two fields are coupled, a disturbance in one can affect the other. The neutrino field is different. It exists in the same space as all the other fields that make up matter. But it is only very weakly connected to them. It is like two conversations happening in the same room, in completely different languages. Both are present, both occupy the same space, but neither interacts with the other. That is why neutrinos pass through matter so easily. The atoms in your body are made of fields that respond strongly to electromagnetic and strong forces. The neutrino does not couple to those forces, so there is nothing for it to interact with. It is not being blocked. It is simply not engaging. This becomes clearer when you think about forces more carefully. A force only acts on particles that carry the right kind of property. The electromagnetic force, for example, acts on electric charge. If a particle has no charge, the force has nothing to grip. You can place that particle inside an electric or magnetic field, and it will not respond at all. The neutrino has no electric charge. That alone removes it from almost every interaction that you experience in daily life. Chemical reactions, solid objects, light, friction. All of these are governed by electromagnetism, and the neutrino moves through all of them without effect. The strong nuclear force does not help either. It acts on particles that carry something called color charge. binding quarks together inside protons and neutrons. The neutrino has no color charge, so the strongest force in nature does nothing to it. At this point, two of the four fundamental forces are completely irrelevant to the neutrino. Only gravity and the weak nuclear force remain. Gravity is universal, but extremely weak at small scales, so its influence on a neutrino is negligible. That leaves the weak force as the only meaningful interaction, and the weak force is exactly what its name suggests, weak. It operates at very short ranges and with very low probability. That is why even enormous numbers of neutrinos passing through matter, and result in almost no detectable interactions. But the weak force does more than explain how rarely neutrinos interact. It also defines their identity. Unlike other forces, the weak force has a built-in asymmetry. It does not treat all particles equally. It only interacts with particles that have a specific property, something physicists call flavor. Flavor is not about composition. It is about which interactions are allowed. Neutrinos come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each one is linked to a corresponding charged particle, the electron, the muon, and the tau. These pairings are not optional. The weak force enforces them strictly. When a neutron decays, it produces an electron and an electron neutrino. It will never produce a muon neutrino in that process. The pairing is exact, and it is preserved in every interaction. Flavor, in this sense, is not just a label. It is a rule the universe follows. This is why the three neutrino types were discovered separately over time. They are not interchangeable. Each one appears in different processes, tied to its partner particle, and only becomes visible when the weak force is involved. But here is where something unexpected begins to happen. Flavor defines how neutrinos interact, but it does not define how they move through space. And that distinction between interaction and motion, this turns out to be critical, because the property that governs motion is not flavor, it is mass. In the neutrino, flavor and mass do not align the way they do for every other particle physics has ever studied. That mismatch is where the neutrino becomes deeply revealing. Once you separate flavor from mass, you are no longer describing a particle in the usual sense. You are describing something with two different identities that do not point in the same direction. Flavor tells you how a neutrino behaves when it interacts. Mass, however, determines how it travels through space and how its internal quantum state evolves over time. It exists as a superposition of three different mass states at once. At creation, they are synchronized, but as soon as the neutrino moves, they start to drift apart. The reason is simple. Each mass state evolves at a slightly different rate. Heavier states change faster, and over time, the perfect alignment begins to break down. Think of it as three musical notes played in harmony. If each is slightly out of tune, they gradually drift out of sync, not because of external interference, but because of their own internal evolution. This internal change is the key to understanding the neutrino's unique and mysterious nature in our universe. The same thing happens inside a neutrino. The three mass states that make up the neutrino begin in alignment, producing a specific flavor. But as they drift out of phase, the combination changes. The neutrino that started as an electron neutrino slowly transforms into a mixture that can behave like a muon neutrino or a tau neutrino if it interacts. This process is called neutrino oscillation. It is not caused by collisions. It is not triggered by external forces. It is an internal quantum mechanical effect, an inevitable consequence of the neutrino structure. The flavor identity is not permanent. It is a temporary configuration that evolves as the neutrino travels. Given enough distance, the process can even reverse. The components can drift back into alignment, restoring the original flavor. The change is not random. It is periodic, predictable, and measurable, and it has been measured. Neutrinos produced in the sun, for example, begin as electron neutrinos, but by the time they reach Earth, many of them have changed flavor. Experiments detected fewer electron neutrinos than expected, which initially seemed like another problem, another missing piece. But the missing neutrinos were not gone. They had simply transformed into other flavors that the detectors could not see. When new detectors capable of observing all neutrino types were built, the total count matched predictions exactly. The deficit was not a failure of theory, it was evidence of oscillation. Similar results have been observed with neutrinos produced in the atmosphere and in nuclear reactors. Across different experiments, different distances, and different energies, the same pattern appears. Neutrinos change flavor as they travel, and this leads to a conclusion that cannot be avoided. For oscillation to occur, the mass states must be different. If all three masses were identical, the components would evolve in perfect lockstep, and no change would happen. If the masses were zero, the same result would follow. There would be no drift, no oscillation, no transformation. But oscillation is observed, which means the neutrino must have mass. And that single fact creates a problem that goes far beyond the neutrino itself. Because according to the standard model of particle physics, the most successful theory we have, the neutrino should not have any mass at all. Not a small mass, not an undetectable mass, exactly zero. And that contradiction is not a minor detail. It is a direct conflict between theory and observation, sitting at the foundation of our understanding of how the universe works. This is where the neutrino stops being just an unusual particle and starts becoming a problem for the entire framework of modern physics. Because the standard model is not simply a collection of observations. It is a carefully constructed system built on symmetries and rules that dictate how particles and forces are allowed to exist and interact. Every particle in that system has its properties generated through mechanisms the model fully describes and understands. Mass, in particular, is not something particles simply have. In the standard model, mass comes from interaction with the Higgs field. This field fills all of space, and particles acquire mass depending on how strongly they couple to it. A strong coupling produces a heavy particle. A weak coupling produces a lighter one. And if there is no coupling at all, the particle remains massless. For the neutrino, the standard model predicts exactly that, no coupling and therefore no mass. Not approximately zero, precisely zero. And this prediction is not arbitrary. It follows from a deeper structural feature of the model, something called handedness. Handedness describes how a particle's spin is oriented relative to its direction of motion. If the spin points in the same direction, the particle is moving. It is called right-handed. If it points in the opposite direction, it is left-handed. For most particles, this distinction is not fixed. You can always imagine observing the particle from a different frame of reference where its motion appears reversed, flipping its handedness. But for particles moving at the speed of light, this is no longer possible. Nothing can overtake them, so their handedness becomes absolute. It is a permanent property, not dependent on perspective. The standard model includes only left-handed neutrinos. There is no right-handed neutrino in the theory. This was not seen as a gap when the model was developed. It was a reflection of observation. Every neutrino interaction ever measured involved only left-handed states. Aim, see, and see, they, and sane, and sanes. That's because the weak nuclear force, the only force neutrinos meaningfully interact with, couples exclusively to left-handed particles. Right-handed neutrinos, if they exist, would not interact through the weak force. They would not interact through electromagnetism or the strong force either. They would be completely invisible to every known interaction in the standard model. And that is where the problem emerges. The Higgs mechanism requires both left-handed and right-handed states to generate mass. It connects the two, and the strength of that connection determines the particle's mass. Without a right-handed partner, there is nothing for the Higgs field to connect to. Within the standard model as it stands, the neutrino must be massless. But experiments tell us otherwise. Neutrino oscillation, this continuous shifting between flavors, can only happen if the mass states are different. And different mass states mean non-zero mass. The evidence is clear, repeatable, and precise. The neutrino has mass. That leaves only two possibilities. Either the standard model is incomplete, or the neutrino's mass comes from an entirely different mechanism. One proposed explanation is the seesaw mechanism. The heavier an unseen partner particle is, the lighter the neutrino we measure. This could help explain why matter exists at all, why the universe did not collapse into a perfect balance of matter and antimatter. The neutrino is a signal that our current understanding of reality is incomplete. It points toward a deeper layer of reality we have not yet uncovered. The Standard Model has been remarkably successful. It has predicted particles before they were discovered, described interactions with extraordinary precision, and provided a framework that has held up under decades of experimental testing. But the neutrino does not fit cleanly inside it. It sits at the edge of the model, behaving in ways that suggest there is more to the story. And that raises a deeper question. If the neutrino does not fully belong to the Standard Model, then where does it belong? One possibility is that the neutrino is connected to physics at energy scales far beyond what we can currently reach. The seesaw mechanism, for example, suggests that the neutrino's tiny mass is linked to the existence of an extremely heavy partner particle. If that partner exists, it would operate at energies close to those present just after the Big Bang. That would make the neutrino more than just a particle. It would make it a messenger from the earliest moments of the universe. Another possibility is even more unusual. If neutrinos are their own antiparticles, then the distinction between matter and antimatter is not as rigid as we once thought. That would allow for processes where matter can effectively transform in ways the Standard Model does not currently allow. And that has consequences, because one of the biggest unanswered questions in physics is why the universe contains more matter than antimatter. According to our current understanding, the Big Bang should have produced both in equal amounts, leading to mutual annihilation, and yet matter clearly dominates. Something must have created that imbalance. If neutrinos behave differently from other particles, if they violate certain conservation rules under the right conditions, they could be part of that explanation. The existence of galaxies, stars, and everything built from them may trace back to processes involving neutrinos at energies we cannot yet recreate. This is why experiments searching for neutrinoless double beta decay are so important. If that process is observed, it would confirm that neutrinos are Majorana particles, particles that are their own antiparticles. It would also show that certain conservation laws, once thought absolute, can be broken under specific conditions. That would not just refine our theories, it would force us to rebuild part of the foundation. And this brings us back to where the neutrino began. It started as a discrepancy, a gap in an energy calculation that refused to disappear. It was proposed reluctantly, detected with difficulty, and then revealed to carry properties that challenge the very theory used to describe it. At every stage, the neutrino has been defined not by what it does, but by what it does not do. It does not interact with most forces. It does not leave tracks in detectors. It does not behave like other particles. And it does not fit neatly into the framework we built to understand the universe. But those absences are not empty. They are clues. Because sometimes the most important information is not found in what is visible, but in what is missing. The neutrino forces physics to confront that idea directly. It shows that even our most successful theories can have blind spots, places where something real exists, but the theory has no language to describe it. And that is what makes the neutrino so valuable. It is not just another particle to catalog. It is a question embedded in reality itself. A question about mass, about identity, about the structure of forces, and about the origin of the universe. Every neutrino passing through you right now is part of that story. Invisible, almost undetectable, yet carrying information about processes happening deep inside stars, inside reactors, inside the earliest moments of the cosmos. You will never feel one. You will never see one. But their existence is quietly reshaping how we understand everything around us. And that is the real significance of the neutrino, not what it is, but what it reveals.